low. That's it. That's the message. The very first message sent over the first internet connection between the University of California and Stanford in 1969. The line was supposed to be login, but the network crashed. Things have gotten a bit better since then. Today, we send billions of messages every second across the internet. Marketing teams can track click streams to analyze customer behavior. Agricultural companies receive real-time data from their combines. And turbine manufacturers pull engine readings mid-flight. So, lo and behold, we're talking data streaming. How does a regular organization, say a car rental company, understand what's going on with their business? How are sales doing? What about car inventory in each of their branches? What do customers want? They build data analytics pipelines. There are always data sources. For instance, these may be a point of sale that records transactions, a CRM that keeps customer details, and a website analytics service that collects traffic and user behavior information. Each of them has its database. Consider that a company craves learning how customers of different age groups behave on a website. Every month, a data processing engine sends API requests to a CRM and a website analytics system to pull this data. These services take monthly records from their databases and pack a response. Once the request is satisfied, the connection halts. Then this data is processed to match customer records from the CRM with the website sessions and saved in some storage. It can be a database or data warehouse. The records are analyzed with business intelligence tools. Finally, you have a report saying something like, Gen Zs don't read copy. Let's make our landing page all videos. The takeaway here is that the business gets data on a schedule, every month, every week, or even every hour. This approach is known as batch processing. You collect some data over time and process it in batches. Simple. But what happens if a company needs to know the current vehicle locations? Or if they want to figure out if their customers are overspeeding? Or a utility company must track the ongoing electricity consumption? Or a social media company tracking user behavior and engagement? You need real-time updates on what is going on and the best-case scenario, the ability to interpret them right away to make decisions. Should we send the customer a notification reminding them that overspeeding is dangerous and now they are paying extra for reckless driving? How much electricity throughput do we need given that the consumption is currently rising? Which posts and videos should we prioritize now to keep a user engaged? Batch processing doesn't work for any of these cases. To approach them, you must first change the way you think of data. With batch processing, your information is transmitted in rather big messages written in, say, XML or JSON formats. These messages focus on describing, well, things, or people, or things about people, also animals. Okay, you get the idea. For example, this is Judy. She spent 5 seconds on the landing page with copy requiring 15 minutes of reading, scrolled 85% of it, and left the website for good. This is her ID, IP, browser, location, operating system, and screen resolution. Things. They describe Judy's rude visit to a page that your team had been approving for 3 weeks. This message would be a normal one for batch processing. If you need to track Judy's actions to know what she's doing every second in real time, you think of events. So what are those events? To understand what an event is, you need a dictionary, because events in programming aren't conceptually different from events in real life. Instead of gathering a whole dossier on Judy's visit, events are recorded in a sequence of smaller messages. The message would have a key, some event data, and a timestamp. Here's Judy landing on a page at 2:21:15. Now she's scrolling at breakneck speed to the bottom of the page at 2:21:17, and she's gone at 2:21:20. The structure of event messages can be more complex, containing extra details like metadata about a browser and operating system. But the idea stays the same: capture the changes in the state of things. These event messages are the foundational actors of event-driven architectures and data streaming pipelines. Let's say Judy didn't read the copy but still rented a car. We can track a vehicle's location with a driver app sending GPS coordinates. For a fancy logistical or car rental company, this may be a telematics module collecting a lot of readings, including GPS coordinates, speed, and engine data. Our analytical system could request the telematics module for data every second and wait for a response, but that would be slow. This doesn't work this way. Let the module push information to the analytics system. While you can send thousands of messages from data providers to data consumers directly, it doesn't mean that downstream analytical systems can always process them in time. Some messages would get lost. If we must chain, say, engine readings in some sequence, lost data can lead to errors. You're looking for some mediator, a stream processor that would help downstream systems consume those events at their own pace and in the right order. So what does a data streaming processor look like? We need a system optimized for writing, thought Jay Krebs, formerly an engineer at LinkedIn and now a co-founder of Confluent. And since he happened to like Franz Kafka, Krebs gave the author's name to the stream processor. Despite Franz Kafka wanting all his work burned, his final metamorphosis into the most popular streaming tool aims at the opposite, writing messages in queues and storing them. There are other streaming platforms like Amazon Kinesis or Google Cloud PubSub. Interesting naming. Let's get back to it soon, shall we? But their underlying principles are similar to Kafka's. Imagine we have a fleet of vehicles producing 3 different types of event messages: GPS coordinates, speed, and engine readings. On the consumer side, a maintenance service wants to know the coordinates to allocate spare parts across different locations, along with speed and engine data to capture possible technical failures and prepare for downtime. So far, so good. Data producers or vehicles send messages, while a streaming engine writes these messages in a queue for the maintenance service to consume them. Think of a queue as a long log file. But what if we also have a dispatch service that needs speed and coordinates but doesn't deal with engine readings? And there's also a policy service that just wants to know whether the driver is overspeeding. If every service reads from the same queue, we still have a mess because they need to do extra work and filter unwanted messages. To avoid that, Kafka and other engines direct those messages to separate streams or topics. So you have 3 topics: coordinates, speed, and engine. Now, every service can subscribe to their topic of interest. Maintenance subscribes to all 3. Dispatch subscribes to speed and coordinates, while policy consumes only from the speed. Remember Google Cloud PubSub? Yeah, it means that providers publish messages to different topics, while services subscribe only to those topics that they are interested in. Great, we have a streaming pipeline. But remember, when it comes to data processing, the main word to learn to sound competent is scalability. What if each vehicle is unique as a snowflake, a personality on its own? What if it deserves individual treatment and a digital twin to simulate all malfunctions in advance? You'd better have an exclusive service for each. With a streaming processor, you can divide topics into separate partitions, each dedicated to messages having the same keys. In this case, each vehicle can have its own partition. A service dedicated to maintaining a truck called Bob would subscribe to the coordinates topic and read from the Bob partition. The service taking care of the vehicle, Charlie, reads from the Charlie partitions. And the same for Rory, Luke, and the rest of the vehicles. If Bob's service goes down or suddenly receives fewer computational resources, the remaining fellows can take over this partition. Besides all that, imagine that our fleet operates in different regions or across different continents, planets maybe. You don't want to put the same topic in one place, on a single server. The partitioning system allows for distributing the same topic across multiple server clusters in different parts of the world, on different planets, and facing no limits to the topic size. Now you have scalability. But streaming architectures can be way more complex. You've noticed that the term service has been mentioned more than once. Streaming systems were designed with a microservice architecture in mind. This means that instead of having a monolithic system doing everything, it's broken down into independent modules. They all can use PubSub to communicate with each other. Maintenance can publish messages on vehicles that are being currently repaired to its own topic. And dispatch would subscribe to this topic to know which vehicles are available. Now imagine you have dozens of services. And if all of them must communicate, send messages one to many and read many to one. Remember the request-response model? Yeah, now consider how hard that would be if all of those services were using it. Suddenly, everybody waits for everybody. That's bad, not scalable. That's why even if you don't exactly think of real-time data streaming, but you do have a large microservice architecture, the pub/sub approach may look like the way to go. Stream processing is an exciting technology, but what about getting insights from these data streams? How do streaming analytics work? It's a matter of what your analysis systems look like. You may have a live business intelligence dashboard built with Power BI, Tableau, or other software of your choice. A BI tool caches a small amount of streamed data to display right away and then deletes it. This doesn't allow your specialists to analyze historical data or build custom reports, but it works for detecting ongoing events and reacting to them right away. For example, your policy service may track whether vehicles are overspeeding. Or you can have a machine learning system analyzing the data stream on the go, and then sending results to business intelligence or other applications. A dispatch service can use an ML model to analyze the current speed and location to adjust an estimated time of arrival. For instance, your maintenance service can read a stream of engine readings, complementing them with such batch and rather static details as the model, time in service, or the dates of the last check to yield better insights. You still don't want to lose your data, so regardless of whether you analyze it on the go, it still can be saved in a database or warehouse or a data lake to support batch analysis later. And if you want to know more about how data is captured and processed to yield business insights, check out our video on data engineering. As data science and machine learning get all the credit, we pay tribute to the essential workers of the analytics pipelines, data engineers. If you like this video, give it a thumbs up. And if you want to learn more about data processing and analysis, just let us know in the comments. Thank you for watching.